back to Math260. This lesson today, Lesson 7, is on matrix arithmetic properties, or arithmetic properties. And just to remember what we did in the previous lesson, if I have a matrix, let's say A, two by two matrix, the elements are 4, 7, 3, and 6. If I multiply this matrix by a constant, what it does is multiplies every element, just like vectors by a constant. So if I take 3a, I simply multiply each element by 3, and that gives me the matrix. 3 times 4 is 12, 3 times 7 is 21, 3 times 3 is 9, and 3 6s are 18. So that's matrix 3a. And if I make a new matrix B, of the same size, like that, and I compute A plus B, I do it just like vectors, I add element by element. So it's 4 plus 2 is 6, and 7 plus negative 2 is 5, and 3 plus 4 is 7, and 6 plus 4 is 10. So that's the sum of those two matrices, adding element by element. But we're going to explore how does these two operations, scalar times matrix and matrix plus matrix, how do these operations behave? It turns out, because these are defined almost exactly like the vector operations, that is, we add element by element, and we multiply by a scalar. We simply multiply every element. We're going to get the exact same results. So let's list the properties. By way of reminder that we get, and also look at the proof of a couple of them. So we have the following. For matrices of the same size, that is, if this is 3 by 2, then it has to be 3 by 2. Matrix addition is commutative. Doesn't matter whether I take A plus B or B plus A, I get the same answer. Just list these in the same order. If I add the matrices B and C, take that result, and then A plus that, I get the same thing as if I add A and B first, and then add the result C. That's the associative property of matrix addition. Property 3 is if I take the matrix A and add the zero matrix of the same size, that is, that's not, again, not the number 0, but a matrix of the same size where all the elements are 0, I get the matrix back. And so the zero matrix acts as the identity matrix. And then finally, for additive properties, A plus negative 1 times A, well, that simply negates all the elements of A and adds it to A, so I get the zero matrix as the result. And this can also be written as A minus A, shorthand for A plus the negative of A. So these four are the same as those four vector properties that we had, properties of matrix addition. It's commutative, it's associative, there's an identity, matrix full of zeros, and every matrix has an additive inverse. Simply multiply all the elements by negative 1. And then properties 5 and on include scalar multiplication. So just to maintain compatibility with the book, we have if I add two matrices, take that answer matrix and multiply it by a scalar, I get the same result as if I multiply each matrix by the scalar and add the two results. So that says that scalar multiplication distributes over matrix addition Property 6 is similar. If I add two scalars, two real numbers, take that answer and multiply by the matrix, I get the same results as if I take the first one and multiply it by the matrix, take the second one and multiply it by the matrix, and add those two matrices that result. So here the addition is real number addition. Here the addition is matrix addition, but I get the same answer either way. And this says that scalar multiplication distributes over scalar addition. Property 7, just like the vectors. If I multiply a matrix by a scalar, get the answer, which is a matrix, and multiply that new matrix times the scalar r, I get the same result as if I multiplied the scalars first, and then took that answer and scaled the matrix once. So again, here the multiplication is real number times matrix. Here the multiplication is real number times real number. But I get the same answer either way. It's called the compatibility of scalar multiplication. And finally, 8. If I multiply the scalar 1 times the matrix A, that says multiply all the elements by 1. So of course I get the same answer. That acts as the multiplicative identity for scalar multiplication. So these are the 8 properties. They're the exact same properties as we had for vectors. If I replaced A, B, and C with U, V, and W as vectors, it would look exactly the same. And so the conclusion is that for a fixed set of dimensions, the set of all matrices of a fixed dimension, like the set of all 3 by 5 matrices, or the set of all 7 by 2 matrices, whatever. Once I fix the dimension, I take all those matrices, and if I include this addition and scalar multiplication, what I have is a vector space. So here's our second example of a vector space. We saw that the set of vectors of a fixed size with addition and scalar multiplication was a vector space because that's what I'm doing, adding vectors. In this case, my vectors, my quote-unquote vectors, are the matrices, but the arithmetic behaves exactly the same way. So now we have our second example of a vector space. And for each dimension, pair of dimensions, I get a different vector space. So how do we prove things like this? Well, we'll just take one example. We'll have lots to work with in the workbook. We're going to just, how would we prove something like this, property 6? It's a similar idea. To prove it in general requires a lot of work, but to prove it for a fixed dimension is not too bad. So let's see what we can do. So let's assume our matrix A is 3 by 3. We'll make it a little more interesting this time. With elements A, B, C, D, E, F, and G, H, I. Here's my generic or general 3 by 3 matrix. And now I want to compute R plus S times A. by definition, I multiply the quantity r plus s by each element. Boring, but you have to write it out to see what happens. Here we go. So there's the quantity r plus s, that's actually going to be a single number when I do the arithmetic, multiplies each of the elements. But each element in here, the way I compute this is with regular old real arithmetic. So what can I do? I can use the distributive law on each one of those. So if I distribute r plus s times a, that's the same as ra plus sa. And similarly on the others. This is legal because I have a distributive law in each of these cases because I'm simply doing regular old real number arithmetic. Ri plus Si, and that ends it. So all I've done now is apply the definition of scalar times matrix, and then use the distributive law of regular old real arithmetic, and I'm here. But that to me looks like the sum of two matrices. Which two? Well, this is exactly equal to, I'll continue up here, I guess. So that's the first matrix plus the matrix with all the S's, right? This looks just like the sum of two matrices. So these two are the same because if I use the rule for matrix addition, I add like terms. Ra plus Sa is the first answer, etc. But now I can do one more thing, because there's an R in every single one of these elements. I can factor it out. That's the same as R times the matrix plus I can pull the S out of this matrix since every single term there has an S in it. But what is this? This is just R times the matrix A plus S times the matrix B, which is what we wanted to prove. So this is always the trick. We define a general matrix, or if there's two of them, we define two general matrices. The other one might have elements P, Q, R, S, T, etc. with different letters. And then I do the algebra and use the properties of the underlying arithmetic, the arithmetic of real numbers, and then work backward. So this is equal to that by definition, and this gives me that by the definition of scalar multiplication. This gives me that by the definition of matrix addition, and then this by undistributing it. So everything's equal all the way along, so I get that R times S plus A works this way. So that's the approach. This is how we prove these properties. Let's use one of them.
15, 14.
Why do we care about these properties? Again, it's algebra. Suppose I have the following expression. What can I do with this? Well, I have a commutative law for addition. 2A is a matrix, so is 3B. So I can switch these around and get 2A minus A plus 3B plus B, right, by commuting these two, because this is really plus negative 1 times A. And if I write it that way, that's 2A plus negative 1 times A, and this is 3B plus 1B. And now by my rule of scalar distribution, this is the same as 2 minus 1 times A, and this is the same as 3 plus 1 times B, the rule we just proved. And now, of course, I can do the arithmetic. So this is just 1A or A plus 4B. So these rules allow us to do algebra just like we do with regular numbers. That concludes lesson 7.